Hello again, here we are in the second lecture on aldehydes and ketones, and we have some mechanisms we're going to draw. And in the first one we have the carbonyl, which is going to go grab the hydrogen off of the acid to form the protonated carbonyl. And then we have our methanol, which will then attack the protonated carbonyl. In this reaction we don't have a good nucleophile, so we have to make the electrophile better, which is the carbonyl. So we protonate it, and then that gets us to the hemiacetal, which we talked about in the last lecture, and then or the protonated hemiacetal, and then methanol removes the extra hydrogen off of it to give us the hemiacetal, excuse me. And then in the second one we get the same thing, where methoxide adds into the carbonyl. Methoxide is a good nucleophile, unlike the methanol from above, which gives us the negative charge on the starting carbonyl oxygen, OMe, and our hydrogen is still there. And then in the second step, that will go grab a hydrogen off of the acid to get us to our final answer. In the third one, we're going from the carbonyl, and it will go through the hemiacetal that we saw up in the first mechanism on this page, and then go from there. So the first step we have to do is protonate the carbonyl, and then methanol will add into the carbonyl to give us the protonated hemiacetal. And then we remove the extra hydrogen from the hemiacetal. And then we see that we have to go from having the OH and an OMe to getting to our final answer, having two OMe's on the carbonyl carbon equivalent. So we have to turn the other OH into a good leaving group by protonating it. And then remember, since this is the aldehydes and ketones carbonyl chapter, we have to go through the carbonyl equivalent to kick out the good leaving group. And then methanol adds to the carbonyl equivalent to give us a protonated acetal. Put the positive charge down here, and then all we have to do is remove our extra hydrogen from the protonated acetal, and we are there in our final answer. Here, let's separate these out so it makes more sense. And just like always, if you have any questions, feel free to send me an email to ask about whatever you're wondering about. I want to make sure everybody does well. Here we have another mechanism where we have the Wittig, and in the Wittig, the first step is the base comes and grabs the hydrogen to give us the anion on the carbon, and then that is our good nucleophile, which adds to the carbonyl. Which gives us this, which can then form a four-membered ring. And then remember, when one of the four basic principles of organic chemistry is what we'll use here, where remember what they are. We have pKa's, electronegativity, sterics, and resonance. And in this, we see we need to form a carbon-carbon double bond between the two carbons, and we no longer have the carbon-phosphorus bond or the carbon-oxygen bond. So those two bonds have to break. So when we think about them, the best way for them to break is where the oxygen, which is more electronegative than carbon, is going to pull the electrons towards it, and the carbon is more electronegative than phosphorus. So when that bond breaks, it'll go towards the carbon, giving us our desired product. Okay, the next one here, the reduction of a carbonyl, may take extra space than what we have here on the page, so we'll just see how it goes. But the first thing that happens is we have hydrazine, and our hydroxide can pull off a hydrogen off of the hydrazine to give us a good nucleophile. This good nucleophile can then add to our carbonyl, which gives us this species, which we can then protonate here off of the water we just formed. And then we can remove the hydrogen off of the nitrogen to give us a negative charge out there. And then from here we can form a double bond and kick off our leaving group, which gets us to this, and we'll have to add a page in here to continue on in the mechanism. So we'll start there with that structure, redraw it on the top of the next page, and then go from there. So on the last page we had this. Then we also had hydroxide around, and hydroxide can grab the hydrogen off of the N nitrogen to give us a negative charge out on that nitrogen with its two lone pairs and a hydrogen. It's got a bond to that other nitrogen, which is then double bonded to the carbon, which has the methyl and the hydrogen still on it. Now we can draw a resonance structure of this where we form a double bond here and break that double bond and have the nitrogens with a double bond, a single bond to the carbon. Carbon has a negative charge on it now, and then we have the methyl and the hydrogen. This negatively charged carbon can go grab a hydrogen off of our water that we formed in the previous step, giving us the double bond between the two nitrogens, single bond to carbon, which now has two hydrogens and a methyl off of it. And then we can see the hydroxide that we just formed in the previous step reacting with that to remove a hydrogen off of our N nitrogen, which gives us a a negative charge on that N nitrogen with a double bond to the other nitrogen. It has a lone pair, two lone pairs out here on the end if you want them. Then our two hydrogens and our CH3 off of the carbon. And then we can see the negative on the nitrogen forming a triple bond, kicking out the CH3 minus, which gives us nitrogen gas, which is going to bubble out of the solution, along with CH3, CH2 minus, which can grab a hydrogen off of water, and that gives us our end product of ethane. And it doesn't matter what the starting carbonyl is, the mechanism is going to be exactly the same. Here we have some keto-enol tautomerizations. If we add base to a carbonyl, the base is going to grab a hydrogen off of it to form the enolate. And then that enolate can go grab a hydrogen off of deuterium D2O, and as it does that, we end up getting to our deuterated carbonyl equivalent. Okay, now in this we can do the same thing with regular water or deuterated water, it doesn't matter, but we remove a hydrogen off of our alpha carbon, forming the enolate, and then reform the carbonyl, having our enolate go grab a deuterium off of D2O. We know we have D2O because our DO minus has to be in a solution of the same deuterated solvent as it. If we put it in H2O, all we'd end up with is a big mixture of DO minus and HO minus in solution. So we have to be careful about that. In the next one here, we have acidic D2O. So the first thing that happens is we have to protonate our carbonyl, and then we can remove the hydrogen, forming the enol, and then the enol can go grab a hydrogen or a deuterium, whatever you're going for. In this solution it's deuterium, to give us the deuterium on the alpha carbon. And then all we have to do is remove the extra deuterium off of our carbonyl with D2O, and we get to our desired product of the alpha deuterium compound. In the next one, we have excess iodine and hydroxide in a carbonyl with an alpha methyl. So the first thing that's going to happen is our hydroxide is going to go grab a hydrogen to form the enolate. And enolate, sorry. And then the enolate will go grab an iodine to form the alpha iodo, which we can pull off a hydrogen off of this with hydroxide to form another enolate. With one iodine, one hydrogen, and our double bond, and then that can go grab another equivalent of I2, kicking out an iodine to give us the diiodo compound. And then all we have to do is one more time grab that hydrogen, form a third enolate, and then we can put the third iodine on there by having this go grab one more equivalent of I2. Now I need to add a page here, so on the next page I'll draw the product for this, and then we'll go on to finish out the reaction to form the carboxylate. So at the end of the last problem, we formed the triiodocarbonyl. Hydroxide can then add into the carbonyl to form this, and then we can reform the carbonyl and kick out the leaving group. This makes a decent leaving group in this example, because while the negatively charged carbon has 3 iodines on it, the iodines are more electronegative, pulling the electron density towards the carbon, so it stabilizes the negative charge, and then that can go grab the hydrogen off of the acid we just formed to give us the iodo form, along with the desired carboxylate. So here we have hydroxide, and this is an aldol reaction. You've seen this earlier in Org 1, those of you that had me for Org 1. We had it as an example on an old test of predict the products for each of the steps as you're going along. But our base is going to go grab a acidic hydrogen to form an enolate. And then our enolate can react with benzaldehyde to form a carbon-carbon bond. That gives us a negative charge on the oxygen of what was our benzaldehyde, reforming our carbonyl. This can now go grab a hydrogen off of water to give us the alpha hydroxy carbonyl, and then from here we can draw it in either an E1CB or an E2 elimination, where hydroxide comes in and grabs the hydrogen off of that acidic carbon, and then once we form the negative charge, we can kick out the leaving group to form cinnamaldehyde. In the second mechanism here, it's going to be exactly the same as what we just did. We're going to pull off a hydrogen off of our alpha carbon. We know the alpha carbon is the only one with an acidic hydrogen because we can draw resonance structures for the negative charge, moving it around. And then that will react with the benzaldehyde to form the carbon-carbon bond. And then we can grab the hydrogen off of water to protonate that. To form the beta hydroxy ketone. And then we can do either the E2 or the E1CB, like we did in the previous step, where E1 it's an E1 elimination with CB being the conjugate base. So if we draw another, we have the base coming in to grab that hydrogen, forming the negative charge. You can draw it as the enolate or just with the negative charge on the alpha carbon. They're just resonance structures of one another. And then we can kick that out to form our desired product of that. E1CB